Our second conic section that we are going to study is an ellipse. We have 3 objectives here for studying ellipses. First, when you're done with this unit, I want you to be able to graph an ellipse. I want you to be able to write equations of ellipses, and I want you to be able to solve applications involving ellipses. Let's talk about what an ellipse is. I always joke with my husband and sometimes my kids' teachers at school when they were in preschool how my kids don't call ovals ovals. Most kids, when they're learning their shapes, they learn circle, they learn triangle, they learn square, they learn oval. No, my kid learns ellipse instead of oval. So that's really what you get. That's really what we're talking about when we see an ellipse. But it's a very specifically shaped one, so I don't want you to, I want to be clear that there's a specific definition to an ellipse. An ellipse is the set of all points such that the sum of their distances from 2 fixed points, which we call the foci, is a constant. I hope this picture over here in the corner kind of shows you what we're talking about. If you pinned this rope at 2 different places and stretched it out to so that this distance here is always constant. It's whatever the length of that yarn or rope or whatever is. That will give you an ellipse as you rotate that around, right? This point over here, when you go from the foci to that point and back to this point, is the same as this distance because this rope is the same length the entire time. Or even one way over here, if you add up here, this distance here, and then this distance all the way over to that. That's what an ellipse is, sort of graphically. And algebraically, we write this equation in this form. Standard form of the equation of an ellipse with center at the origin, major and minor axes of length 2a and 2b, a squared is greater than b squared, is this, x squared over a squared plus y squared over b squared is 1. If the center is not at the origin, we're going to require some horizontal and vertical translations. Let's see here what we're talking about. This picture shows, I want to be clear that this is not necessarily the origin. That is the center of the ellipse here. If the center of the ellipse is HK, that's that shifting left and right, up and down. Notice these are both the same. What I want you to be thinking about here is in this picture, the A is the distance from the center out to this edge of this ellipse. That's the A. B is the distance along the minor axis. So it's from the center out to this point. That, in this case, is under the Y. I don't want you necessarily to memorize all these formulas. What I want you to think about is the larger denominator is under the X term. If that is true, you get a horizontal ellipse, meaning it is wider than it is tall. The bigger number goes under the X in a horizontal ellipse. Over here, the bigger number goes under the Y in that vertical ellipse. So the bigger distance gets squared and goes under the appropriate variable. Hopefully it makes sense to you that if this distance is A, that bigger distance is A, it's vertically bigger. We're going to put that under the Y. Always equal to 1. Always a plus sign between there. Coefficients on the x squared terms and the y squared terms is 1. Okay, here's the information. These are identical over here. The difference is the vertices. When we're talking about vertices, you are talking about these points here at the edges. So you take the center, the H, and add A to it and subtract A. That'll give you these 2 points, these A points out here. So that's this, H plus or minus A. The Y value is the same. These B points come from taking the K, the Y value, and adding B and subtracting B. So that's this. Again, don't memorize this. I think you can figure that out sort of logically. What you may need to sort of memorize is the distance out to the focus. Each of these focal points are a distance of C away from the center. And the relationship between A, B, and C is given here. In this case, we're going to add C and subtract C from the X coordinate, the H, of the center to get those points. Same thing is true over here, but everything is now kind of switched. So you add and subtract C to and from the K, the Y coordinate, because you're going up and down from the center. Okay? So don't memorize this. I think we can figure it out. This is the one thing that you may need to really know. I don't necessarily have it memorized in that form. I think of this as C squared equals A squared minus B squared, which means B squared plus C squared equals A squared. And that is intuitive to me because which of these distances is the biggest in these examples? A, B, or C? Well, A is this length along the major axis in both of these pictures. It's the biggest number. B is shorter because that's the minor axis, the shorter axis. And C is some distance shorter than A because the foci are in between the center and that vertex along the major axis. So I don't really necessarily memorize this. I just know that the A is the biggest distance, so it has to be the one that's by itself with the other two added. And this all boils down to a Pythagorean theorem. That's kind of where it comes from. The question is always with the Pythagorean theorem, though, the biggest distance is the one by itself, right? In that A squared plus B squared equals C squared. It doesn't really matter what letters you use. A squared plus B squared equals C squared would better be stated leg squared plus leg squared equals hypotenuse squared, where the hypotenuse is the biggest. It always has to be the one by itself, the biggest distance. Okay, foci always lie on the major axis, C units from the center using that relationship that we just talked about. Let's try to do this, and let's try not to refer back up there too much, but kind of try to logic through it. It's really a lot to memorize. It's really much harder to understand conic sections if you try to work through them by memorizing all the stuff, because you will just mix it up because they're very similar for ellipses and hyperbolas and subtraction and whatever. So you will have to do things like memorize the general form of the formula for an ellipse. 0, 3, I'm just plotting these points. 0, -3, those are the foci. Vertices at 0, 5, and 0, -5. The first thing I know is that this has to be a vertical ellipse because the foci are on the major axis. What I really need to graph this, these are my vertices, so that's how far out it comes. I just need to know the width of this, and that will give me a good picture. So let's see here. We know that 5, well, first of all, we know that the center will be 0, 0 because the center is right in the middle of either the foci or the vertices. We also know that that makes A, what we called A above there, but really I'm thinking of it as the biggest distance, 5. and C is 3. The biggest distance has to be by itself. So 5 squared equals 3 squared plus b squared. That means 25 equals 9 plus b squared. B squared equals 16, so b is 4. What that tells me is my minor axis has length 2 times 4, so I go from the center out 4 spaces. 1, 2, 3, 4. 1, 2, 3, 4. My other vertices, the minor vertices, are going to be at 4, 0, and -4, 0. At that point, I'm able to draw my ellipse. This is actually going to look pretty close to a circle because there's not that big of a difference between the height and width of this ellipse. Should be a nice smooth curve there. That's not super smooth. Okay. The other thing I need to know, I sketched the graph, so accomplished that. The other thing I need to know is the equation of the ellipse. I always remember that, and it doesn't matter if you do x, well, center is 0, right? So there's those. Always addition, always equal to 1 on the ellipse. The denominator is the horizontal distance squared from the center out to the edge. It's this distance squared, which is 4 squared or 16. The denominator under the y is going to be the vertical distance squared. So that's it. More cleanly, this would be x squared over 16 plus y squared over 25 is equal to 1. I don't even necessarily worry about what's my major axis, what's my minor axis. I just know from the center out to the vertex horizontally, that number gets squared and goes under the x term. And same thing for the y, just looking at the vertical distance. Let's try another one. Graph and find the center, foci, and vertices of 9x squared plus 4y squared equals 36. The problem that we have here is that this does not look like the standard form of an ellipse. We want an ellipse, if we're talking about an ellipse, we want it to be equal to 1. It doesn't specifically say here that this is an ellipse. I know this is an ellipse because I have x squared and y squared, both positive, with different coefficients here. If the coefficients were the same, it would be a circle. The different coefficients give it that squishiness. I mean, similar, circles and ellipses are very, very similar, right? With a circle, or with an ellipse, I want this written equal to 1. So I'm going to divide both sides by 36 so that I have my equals 1 on the right side there. On the left side, I'll have x squared over 4. I'll have y squared over 9. The first thing I notice is the center is at 0, 0 because I have nothing added or subtracted inside my x squared and my y squared. From the center, I'm going to go out 2 spaces horizontally, and I'm going to go out 3 spaces vertically. That's really it. Those came from under x, I have 4. So that means the square root of that is 2. That's the distance from the center out to the vertex. Under the y, vertically, I'm going to go 3. The square root of that, 9. This is my ellipse. Okay, so we have another vertical ellipse. We graphed it. we found the center. Let's write down the vertices. We have them. 2, 0, and negative 2, 0 would be the minor vertices. 0, 3, and 0, negative 3 would be the vertices on the major axis. The last thing we need are the foci. I know they are going to be somewhere along the y-axis between 0 and 3, and the same distance between 0 and negative 3 away from the center. The way I find that is that idea of that Pythagorean theorem where my biggest distance, 3, is by itself. And I don't care what letters you actually use here. Oops. Technically, we use C in our documentation up there for the distance to the foci, but you could put a smiley face there. It doesn't really matter. C squared is 5. That means C is plus or minus the square root of 5. From here, the square root of 5 would be a little bit more than 2, right? Because the square root of 4 would be 2. So 1, 2, it's going to be a little bit more than 2 here-ish and here-ish. I don't like this. Oh, man. I'm going to try to connect that a little bit better here. Okay, so we're here and here. Let's write what those ordered pairs are. They're along the y-axis, so x-coordinates of 0, positive root 5, and then the other direction would be negative root 5. That is everything that this question looked for, including the graph over here. Okay, here's a little different one because the center is not the origin. We do have to do that same trick where we're going to divide both sides of this by 4 to give us x plus 1 squared over 4 plus y minus 3 squared equals 1. Technically, if you want to think about it, this is over 1, right? 4 over 4. First thing I'm going to notice is my center, negative 1, 3. Similar relation to if the, with a circle, right? One thing I do want to point out here, we talked about how ellipses and circles are super similar. If this had been a 4 here, if we are given something like this, but with this a 4, you multiply both sides of this equation by 4, and you get exactly the equation of a circle, right? You'd have a 4 on this right-hand side with no denominators on the left side, denominators of 1, hidden denominators, and you exactly get a circle. A circle is just an ellipse where the major axis and the minor axis are the same length. So if these two numbers would match, it's still kind of an ellipse, but with those distances the same, gives you a circle. Negative 1, 3 is here. You know what? I'm going to make my scale a little bigger just to give me a nice picture here. Let's call our scale 1/2. So this will be 1, 2, 3, 4, 5. We'll do the same 1, 2, 3, 4, 5 here. Okay. Okay, and then the negatives this way. Negative 1, 3. That will be my center. Then I want to, let's go ahead and graph it. For me, finding the graph is super helpful. I really need to see the picture to make sense of these. Under the x, I have 4. The square root of that is 2. That tells me to go 2 spaces. Oopsie, forgot my scale was different here. That tells me to go 2 spaces, which would be out here at 1, and over here at -3 for the x values there. Those are my vertices along the major axis. Here, 1 is under the y term there. The square root of that is 1, so I'm going to go a distance of 1 vertically. Notice to find these vertices, what is that? 1, 3, -3, 3, the other ones, let's go from -1, 3, I'm going up 1 space, right? So that changes my y. -1, 4, and I'm going down 1 space. -1, 2. Notice I don't necessarily have to memorize those formulas, but think more about the idea of adding 1 here, adding 2 there, and subtracting, of course. Draw our ellipse. This would have been pretty tiny if we had left our scale at 1, so I'm glad we made that adjustment. We graphed it, find the center. We have not found those. We did find the vertices. The foci will be along this horizontal axis because that is our major axis. 4 will equal 1 plus c squared. So c squared is 3. C is the square root of 3, plus or minus technically. To find the foci, from my center, I need to go to the right a distance of √3. That changes my x coordinate. Leave the y coordinate alone. So -1 plus √3. It's crammed in here a little, hard to see. -1 plus √3, and the y coordinate of this from the center doesn't change, and -1 minus √3. From that x coordinate I'm going, or from that center I'm going right and left, which impacts my x coordinate of those points. Square root of 3 is like 1.7-ish. So I'm going to go 1 space, and that's almost all the way over here, keeping in mind our scale here. So those are pretty close out there to those vertices. That's how we write equations of hyperbolas. That's, ellipses. That is how we find information about these ellipses. It would probably be helpful to know why we care about those things. So we need to look at some applications of ellipses. Stay tuned for the next video where we will do that.